What's going on, guys? Welcome to Netsec Explain. In the last video, we talked about the machine learning process and the theory behind how some of these models actually work. In this video, we're going to see all of that in action by going from raw data to a working machine learning model. All of the code for this video is located in my GitHub with a link in the description below. In here, I've created several workbooks that you can go through so you can play with this code on your own. These workbooks are fill-in-the-blank style with individual tasks outlining exactly what you need to do. In the next several videos, we're going to be walking through each of these workbooks together so that you can see how the machine learning process works in practice. To run these workbooks, you need a Jupyter environment to work with. If you're not familiar with Jupyter Notebooks, they're a really cool way to execute Python code and are perfect for teaching this kind of material. You can run these locally, but here are the two online environments that I recommend. The first is Google Colab. You can open a Colab instance by following the links in the README. Colab is focused on machine learning, and they'll even give you a free GPU to use. In fact, this is the environment that I actually use for my own machine learning research. The only caveat is that you need access to a Google account. But after that, everything's free. The second is called MyBender. You can visit this by going to mybender.org. Bender is focused on more general Python, and you can even build out environments from a GitHub repository. Copy and paste the GitHub repo here, and then set the branch as master. Once the environment is built, here's what it'll look like. The workbook for this video is located in Workbooks, Spam Filter, sklearn. For these next several videos, I'll be using Colab as my environment. So let's hop back over there and open the workbook in playground mode. If you've never used Jupyter Notebooks before, there are two ways to run a code block. You can either press the little play button here on the side, or Shift-Enter. Now, in Colab, when you run a notebook in playground mode, it'll pop up with this warning. This just says that this is user-submitted code and may request access to your Google account. This is just a blanket warning, and no, I'm not asking for any information from you. Colab will also follow up with a second warning message saying that it's going to restart your runtime. Just go ahead and click OK. We're going to go ahead and run this first code block, which just clones my GitHub repo and downloads all of our data. It also sets the variable data dir to point to our data on the system. Let's take a quick look at the libraries we're importing. At the top here, we have our common libraries: OS, string, numpy, random, and matplotlib. After that, we have our natural language toolkit, or NLTK. We're going to use NLTK to collect our list of stop words and to set our stemmer function. Scrolling down, we have our scikit-learn vectorizers, which we'll be using later. Then we have the two models that we're going to be using for this workbook: logistic regression and multinomial naive Bayesian. To wrap it up, we have a couple metric functions, and that's it. Let's run that, and we'll see that the libraries have been successfully imported. We're also going to use this test email, which is just a copy of the email from our slides earlier. We'll be using this email so that we can see how it's transformed at every step of the process. Coming off of the machine learning process, the first thing we want to do is pre-process our data. To do this, we need to define how we're going to tokenize the data so that it's easier to consume for our models. Here, we have our tokenizer function that takes an email as input. We're going to collect a list of punctuation characters and stop words. We're also going to define our stemmer function here. We then use NLTK to split up the email into each word while setting everything to lowercase. And we strip out the punctuation. Finally, we use the stemmer function on all of the tokens and strip out the stop words. Run this and our tokenizer is defined. Okay, we're at our first task. We need to tokenize an email. This one's simple. All we have to do is print out the test email and print the tokens. So we're just going to print test email and then print tokenized email. Pretty straightforward. Here we have our test email and our tokens: East, Asian, font, Lenny, thanks, support, install. Notice we see thank instead of thanks. This is our stemmer function at work. Stemming reduces words down to their root. For example, thanks could have been thank you, thanks, or I thanked somebody today. Dropping down to the root, thank, allows us to treat all three of these words the same. Another thing that I want to point out is that we see unsubscribe in the test email as both capital and lowercase. If we scroll over, we can see that they both show up, but as lowercase and they're missing the E at the end. Now we're ready to load our training data. Go ahead and run this first block. You'll see why in a moment, but first we need to finish our second task, actually loading the training data. We're given 3 steps. Create 2 list arrays, corpus and labels. Read each email in the ham directory and set the labels. And then read each email in the spam directory and set their labels. Creating the list is easy, just bracket bracket for an empty list. Then we can just use a for loop to iterate through each email in ham. We'll append the email to our corpus, and we'll add ham to our labels. From here, we can simply copy and paste these lines of code and change the names from ham to spam. That's it. Run this and task 2 is done. This next block reads some of the counts that we collected earlier. As data scientists, you always want to pay attention to what your data looks like. In this case, we want to see if we have a balanced set, meaning how many spam emails do we have versus how many ham emails. If we had too many ham emails, we may need to make some changes to our data. In the meantime, this looks fine, so we'll just leave it like that. Okay, with our training emails loaded, let's do 2A and view the training data. What it's telling us here is exactly the same as task 1, except we need to print out an email from corpus and print their tokens. Randomly, I'm just going to pick email 12 and see what that looks like. You can pick the same or whatever other index you want. It doesn't matter. We're doing this task to make sure the data is loaded exactly how we expect it to. And sure enough, here we can see LXDE session aborting. And in the tokens, we see LXDE session abort immediately. We have immediately well because there wasn't a space. So our tokenizer thinks that this is a URL instead of picking up on the punctuation. But no matter, it's not going to hurt our model. Now we're on to vectorizing the data. It might sound complicated, but vectorizing is just a fancy way of saying count the words. In here, we're going to use 2 types of vectorizers, count vectorizer and TF-IDF vectorizer. Count vectorizer is pretty easy. It's the straight word count. There's not really much more to it than that. The TF-IDF vectorizer, on the other hand, is a bit more complicated. TF-IDF stands for Term Frequency Inverse Document Frequency. I just call it term frequency for short. But how TF-IDF works is instead of doing a straight word count, TF-IDF uses term frequency to assign each word a weight. The idea behind TF-IDF is that the words that appear all over the place, or pretty frequently, shouldn't be weighted the same as words that don't show up that often. We're going to use TF-IDF and count vectorizer because we don't know which one of these 2 will work best with our data, so we'll try them both. For this task, we need to create the count vectorizer constructor using our custom tokenizer that we defined earlier. Then we're going to use fit transform on our training data and save the output to be used on our model later. In scikit lingo, fit is just code for train, and transform will let us save the results of that training into our countx. I know, it can be a bit confusing using the word train here, but it isn't training our model just yet. What this is doing is collecting our word counts so that we can plug them in later. Do the same thing for TF-IDF. When we go to run it, it might take a few minutes. This is what happens when you try to count every single word across thousands of emails. Once it's complete, we're ready to move on. To give you an idea of what vectorizing looks like, we're going to do tasks 3A and 3B, manually counting the test email tokens and using the vectorizers to do the counting for us. I don't want you to focus too much on the code for either of these. Just look at the outputs and see what they do. In 3A, I'm just going to iterate through all of the tokens in test email and print out their counts. We see East Asian font Lenny, and pretty much every other word only shows up once. The exception being unsubscribe and list.debian.org. Let's see how we can do this with the two vectorizers. Just like in task 3, we need to build our vectorizer with our tokenizer and then fit transform on our list of emails. In this case, it's just going to be a list containing only our test email. Let's do the same thing with tf-idf and run it. Looking at the count vectorizer, this looks exactly the same as our manual word count in 3A. We can even see that indexes 16 and 9 are counted as showing up twice in the email. With the vectorizers, scikit memorizes what word belongs to what index, and this is a way of making the memory space much smaller per word. While we don't know which one is which, what we do know is that 16 has to represent either unsubscribe or list.debian.org. Then 9 would just represent the other. If we scroll down and look at the tf-idf results, we can already see the difference between the two. Instead of a normal word count, tf-idf sets its values to a weight. Looking at 16 and 9, their values are 0.408, while everything else is 0.204. So that's how the count and tf-idf vectorizers work. Let's move on. Now it's time to load our testing data. I've already gone ahead and split up the training and testing data in a 80-20 split. If we look at the testing data directory, we can see that the last extension of each email contains the label ham or spam. So to properly label our data, we're going to need to pull these off. Task 4, load the testing data. This task is very similar to what we did earlier to load the training data. We need to define test corpus and test labels. Then we'll append each email into the corpus array. After that, we'll just pull off the label and add that to our labels array. So let's go ahead and do that. Create the two empty lists and read each file into the corpus array. The labels here are a little tricky, so I'm going to use a regular expression to split the data and then append that to our labels array. I made a couple mistakes in my code here, so just ignore that. Awesome, the data is loaded. Just like last time, we're going to look at the class count for the testing data to make sure that the sets are balanced. This step isn't really necessary here because we have a straight 80-20 split, but it's good practice to make sure that your training data accurately represents your testing data. Okay, task 5. Now to vectorize the training data. To kind of put it into perspective what we're doing here, do you remember in the slides when we were counting the words "a very close game"? We had the 5 sentences that were our training data, and we wanted to count each of the words in "a very close game." So we just split those words up and counted what was in our training data. Well, that's what we're going to do here for all of our testing emails. We're going to use the vectorizers that we already trained and transform the testing data so that we know how often these things show up in our training set. We're going to do the same thing for the count vectorizer and the tf-idf vectorizer. And we're only going to transform the data because we don't want to add the emails to our existing word counts. Go ahead and run that. Whew. We're finally done with preprocessing. And yeah, all that was just the preprocessing step. Now we're ready to train, test, and evaluate our models. I designed this little helper function, generate report, to help us collect some metrics on each of the models that we're going to build. We don't need to worry about what's in it right now, just run the code block and move on. For these next few tasks, what we're going to do is create 4 separate models. These are going to be multinomial with tf-idf vectorizer, multinomial with count vectorizer, logistic with tf-idf, and logistic with count. The reason we're training and testing 4 separate models is because we don't know which one works best. So let's take a look at 6a, training and evaluating multinomial with TF-IDF. In this task, we have quite a few steps we need to take. First, we need to define our multinomial constructor, and then train it with our corpus and labels. Then, we need to run a series of functions with our model. Using our testing set, we're going to generate the model's predictions and its score to calculate its accuracy. We're also going to use those predictions to generate a confusion matrix so that we can see the number of true positives and false positives coming from our model. After that, we're going to generate the classification report, which will give us the precision and recall metrics. In the code, I set up all of these metrics to be used as input for the generate report function. So we're going to need to name these specific values. Set the multinomial constructor as MNB TF-IDF and use the fit function to train it on TF-IDF-X and labels. From there, use the score function to do the same thing with the test X and test labels. Use the predict function to calculate the raw predictions using the test X as input. After that, feed in the predictions and test labels into the confusion matrix and classification report functions. I know, this is a lot of information coming all at once, so I'm going to pause here for a minute and let you take in what we just did. When we run the code, the first thing that we'll see is the classification report. There's more than one way to measure the performance of a model, so the classification report is there to give us some extra information. What I really want you to focus on is the confusion matrix below that. Here, we can see all of our ham emails were correctly classified as being ham, but we also see that nearly half of our spam emails were classified ham as well. Altogether, this gives us an accuracy score of 87.5. Now, that's not too bad, but can we do better? Let's try MNB with Count Vectorizer. In this task, we're going to do the exact same thing, except the only change we're going to make is moving from TF-IDF to Count Vectorizer. Normally, when I give this presentation live, I just copy, paste, and string replace. But for this video, I'm going to type out the code so that it's consistent. And I'll pause here for a moment. Notice how we're using count X when we train the model and test X when we test and evaluate the model. Let's go ahead and run the code. We can see the classification report, and now we're at 94% accuracy. That's quite a bit better. We have a few ham emails being classified as spam, but nearly all of the spam emails are being properly blocked by our filter. This is a pretty good spot, but we're still going to ask ourselves, can we do better? Moving on to the next task, this one's a little bit different than the previous two. In this task, we're going to keep TF-IDF, but we're going to switch out the multinomial function for logistic regression. Other than that, everything else is the same. Using LGS, we need to define our own solver. In this case, we're going to use LBFGS. And I'll pause here for a moment. Okay, let's run the code. At first glance, this might seem a little disappointing. While we only gained a small bump in accuracy, we can see that the model has become a bit more precise. Instead of 26 ham emails being classified as spam, we only have 3. The trade-off here is that a few more spam emails are getting through our filter. So let's go ahead and take a look at our last model and see how we do. For this last model, we're going to use LGS with Count Vectorizer. You should already recognize the pattern by now. We're going to take our LGS constructor and train it on Count X. I'm going to pause here one last time to give you a chance to look at the code. When we run the code, whoa, we nearly have a 98% accuracy. This is the best model by far. Even though 8 of our 590 ham emails are being falsely labeled spam, only 12 of our 270 spam emails are getting past our filter. I don't have exact statistics on modern spam filters, but 98%, that's not too bad. Now that we have our 4 models, we can pick our favorite. Let's put them to the test. I have here an actual spam email that I pulled out of my spam box the other day. What we're going to do is use this modern spam email and see if our filters catch it. This is the last task of the workbook, and it's the hardest by far. Without any hand-holding, what we need to do is use our vectorizers and our models to make a prediction on our test spam email. If you want to test how well you understand everything that we've gone through so far, I encourage you to pause the video here and try it on your own. I'm only going to wait for a little bit, so pause the video right now. Okay, time's up. Here's how we do this. I'm going to set test spam email as the working email in case we want to try this with any other emails we come across. The first thing we want to do is transform the working email using our already trained count and TF-IDF vectorizers. From there, we want to use our 4 already trained models to predict on the transformed data. These models are going to return either spam or ham based on the type of email that they think it is. Oh, I almost forgot. I'm going to need to print out the test email too so that we can see what that looks like. Now, when we run the code and we scroll all the way to the bottom, we can see that the first model predicted the email as being ham and the rest of them predicting spam. Awesome. What we were able to do was go from raw data to a working set of models. We used count vectorizer and TF-IDF vectorizer to see which works best for this type of problem set. And we went through and tried both naive Bayesian and logistic regression to see which model performed better. In the end, we found out that LGS with count vectorizer performed the best overall. Oh, and one last thing before I let you go. Remember how in our formula for multinomial naive Bayesian, we had this alpha character? I know, I kind of hand-waved it in the last video, but we can actually change it to get better results. This is part of the hyperparameter tuning step, and here's how it works. Let's take another look at the multinomial with TF-IDF example. In our original results, we only got 87.5% accuracy. This was the worst performing model in our series. But what if we change that alpha to something like 0.3 instead of 1? When we run that, we can see that it bumped us up to 93.7%. Cool. If dropping it down a little bit to 0.3 helped us out, what if we took this a little further and changed it to 0.1? And here we are, all the way up to 96.5%. With just a little hyperparameter tuning, we were able to take our worst performing model in the series and bring it all the way up to what is now our second best performing model that we've created. Well, that's all I have for you guys today. If you want more information, don't forget to check out the links in the description below, and don't forget to like and subscribe to see more videos like this. I'll see you next time.